So just the second part of this one, still by utilizing the review for the thermodynamic course, we have this theoretical Carnot cycle that we know if it's ideal, we will have this reversible cycle. And here we need some kind of expansion valve to achieve this process. And when it comes to this refrigeration cycle we usually use, and in this part, because earlier we just introduced what evaporator and condenser looks like. Basically, these two are just heat exchangers. And compressor, mechanical device. And for the throttle, later we put a slide there for you to read about that. But for this one, it could just, it's a type of this expansion valve, and it achieves this function of having this hot and high pressure refrigerant coming into this one and get this very huge pressure release and becomes a cool refrigerant liquid state. So there are lots of like charts and tables you can utilize to solve all those problems. So for the pH diagram is one kind that you find out all the values of H, the enthalpy values. And another chart you usually use would be a TS diagram, which is temperature and entropy. And you can convert completely where point 1, so point 1, 2, 3, and 4 is. And in the TS diagram, you will have a constant pressure curve look like this. So you also like for from point 1 to point 2, in the compressor, ideally it would be an isentropic value, isentropic process. So that's the green line that we just showed here. And so in the TS diagram, it would be a vertical line. So you go vertically up and then meet where the pressure of the condenser state is. So you find the point 2 and it goes to 3 and 4. So between the state 3 and 4, you are using the throttle, and it's an irreversible process. So you will see there is a little bit entropy change in this state from the expansion state process. Okay. Anyway, so also you already have all these values like H and S. So that means you can also convert this curve to another diagram, H and S. But this is only just for you to understand like how these 4 processes are changing in terms of like what's the constant pressure, what's the constant temperatures of that. But you don't need to worry too much about these different figures. First of all, you need to get this pH diagram quite correctly, just to make sure everyone knows how to use this one. Because I believe in your assignments, you need to use pH diagram to solve some problems. And another thing, okay, so I'm not sure like how familiar you are with this diagram, but I do find so either you go back to your thermodynamics and find some notes about that, or I did find a website that's quite cute made by MIT. So you can utilize this website to learn more things about this pH diagram, how to read like pressure, enthalpy, temperatures like that. So I just showed you the examples of using this pressure enthalpy chart. Like it's possible you have a superheated state. That might be because your vapor is continuing absorbing the heat from this refrigerated space. But between point 1 and point 2, which is from the compressor, it is an isentropic state, so it must follow these isentropic lines. So you have these constant S values here. And from 2 to 3, constant pressure, as long as you know what pressure it is at the condenser side of this refrigerant. And then from 3 to 4, through this throttle, you have no enthalpy change, but you have a little bit entropy change, if you could recall that TS diagram of that. So some basic steps for you to know how to find all those values about H1, H2, H3, and H4. So that basically is all we need to know for like how to calculate this refrigeration cycle. And so now, as I mentioned earlier, isentropic compressor is ideal. So what if it's not ideal? So like in common cases, in real life cases, we will say there must be some energy loss through this compressor. So what if it's not ideal? And how do we calculate that? So it is still here as it's just isentropic compressor, but if we have some excessive energy loss, then it will move to the right-hand side, and so it becomes more overheated. And these two states are still under the same pressure, so that's the pressure of this refrigerant on the condenser side. So still on this pressure side, you could find these 2 points. So that might be point 2 and point 2, that's the actual state. So you could see, you already know H1 and H2. So this difference is the ideal isentropic compression. And another one would be the actual one. So there is a term that says is the isentropic efficiency. So this parameter is usually given to you, or maybe reversely ask you to calculate that. But for example, if we say we have a compressor, that this compressor has an isentropic efficiency of 80%, then we would know it will be utilized to calculate. Firstly, on the top would be the ideal compression, what's that? Enthalpy change. So that's the ideal one you find from the curve, H1 on H2. H2 minus H1. And on the bottom would be the actual one. So that's H2 bar minus still H1. So that's the equation given to you. So if you know the efficiency, then you will be able to find out where this state is just by looking at the calculated enthalpy and also the same pressure. And reversely, if you know where this is, you can know what's the efficiency of this isentropic, of this compressor. Okay, so that's the difference between these two, the ideal one and the actual one. Okay, so we are almost there, just finish about this part. But the only thing I need to remind, I usually do this in the tutorials, but then I realize you don't really pay attention to the reviews in the tutorials, so I have to move it to the lectures. That there are several tables. If you go and search the information online, for example, you get table 1 here and another table. They are both for R134A. So one thing, just to make sure everyone knows that this table is only for this material, R134A. So it's not universally applicable to all the other materials. And so are the tables. And what I want you to look at is, at the temperature of -40, table 1 tells you the saturated enthalpy is 0, and another one is like 2 to 5. But you have another table. That table tells you at the same temperature, you have a different enthalpy value. So that is like every year students coming to ask me, what's wrong with it? Which table I should use? So now here my question for you is, do you know what's going on here? Do you need to figure out which table you should use, or it doesn't matter?